Thank you, everyone. First and foremost, thank you to the organizers for organizing this meeting over the past several years. I've been in and out this meeting, but these are always wonderful meetings for bringing very bright theorists together. I'm also grateful for the fact that I spend most of my life in the past few weeks just sitting through faculty meetings about budgets and values all day long. So it's nice to actually go and talk about science. So today what I'm going to talk about is some of my larger team's work on doing experiments that allow us to compute using small molecules. So many of you are very familiar with the fact that people have been using different kinds of polymers like DNA to compute and store information for quite some time. What we've been trying to do is basically store and compute using small, unordered mixtures of molecules. And so this is really a different paradigm than most people think about for information storage. So I'll talk to you today about what that storage looks like. I'll talk a little bit about the molecular computation, and then I'll go into some outstanding challenges. What I should especially note is, we're very interested in theory regarding molecular computation and how we can actually optimize these systems. I'll tell you about some ad hoc experiments, ad hoc ways of computing using these systems. But it's a theory that you do that definitely would drive this forward. And so we're always looking to delve a little bit further into the theory there. So the motivation for this is really thinking about how computing has changed over the past, let's say, 70 years or so. So when I was younger, this was a printer that sat in my basement for quite some time. This was a printer. For those of you who are not familiar with these kinds of beats, this was the Fujitsu Facom 655. It was quote unquote super compact, and it can print 340 lines per minute, which is kind of funny nowadays. It was so compact that people like me, when I was 4 years old, I could fit inside this printer. Even as it was printing, I can fit inside and use it as a great hiding place. But this goes to show, exactly what has changed in computing. Obviously, speed has changed, but also size has changed. None of us would imagine using a printer of this size to do anything. These kinds of magnetic tapes used to fill my basement. My father and grandfather were both engineers that used to do these things. And so none of us would think about using these kinds of things for storage, because both computing and storage have essentially grown exponentially in terms of what we can do with them. So this is a little chart that I like to show of calculations per second per $1,000 over the many years. So my grandfather was someone who worked on UNIVAC 1 way back in the 1950s, and that was about 1 calculation per second per $1,000. And as you know, essentially computing power has grown exponentially with time. This graph is a little bit older, but this would imagine us being essentially at the computing power of a human brain at this point in time, which is incredible to think about if you think about what UNIVAC used to be as a computer that filled rooms and was quite slow and extremely mechanical. And so we've seen this growth in computing power that has changed all facets of our life. That's oftentimes enunciated in terms of Moore's law, that the number of transistors per chip will double every 18 months, which will essentially allow us to compute at an exponential pace. But one thing that has happened over the past decade or two is that we've realized that maybe nearing the death of Moore's law, transistors are growing incredibly small, and so therefore it's becoming very expensive to put large numbers of transistors on a single chip. If you think about how much money it costs to make a new fab, that's growing. I won't quite call it exponentially, but it's growing polynomially at least. And there are massive power demands that go along with making chips that are quite this small with so many transistors. And so one might be thinking about how can we actually go beyond maybe the kinds of architectures we've been thinking about to go even smaller, maybe do that with less power. And that's certainly where thermodynamics comes in. The other aspect of what's going on recently is that we're also hitting a crisis in terms of storage. So if you think about how much data we're producing, that's also growing essentially exponentially every single year. We're well into the exabyte, the zettabyte range of how much data everybody's producing and uploading. And so many people would say, well, you don't have to store all that data. Of course, you don't necessarily have to store all the data, all the crazy YouTube videos or Netflix that people are producing. But you might want to store a large component of that. And even so, if you want to store that components of it, those components are still growing essentially exponentially. And so that leads us to ask the question, can we do something for storage and computing that's different, that can go smaller and maybe ultimately store more things? And so one possibility is thinking about molecular storage and computation. If you think about molecules are in fact smaller than most transistors that we can think about. So if we're talking about transistors being of the scale of, let's say, 5 nanometers or slightly smaller, at that point, quantum mechanics starts to take hold, and that sometimes makes it very difficult to store information. But molecules themselves are smaller than let's say 5 nanometers or 3 nanometers. Many molecules will be smaller than those kinds of dimensions. And so why not potentially use molecules to store to get smaller? And as we know, you can also talk about different thermodynamic limits of using molecules to do different things. So why not potentially compute using molecules? And so if you're not familiar with these ideas, molecules are nice in the sense that molecules are found everywhere. Now, for people that use DNA, we know that DNA is widely found, but if you think even more broadly than DNA, molecules obviously make up our environment. And so you could potentially think about how could you use molecules that we would just find in our environment. We don't have to synthesize them. We don't have to do really anything to do storage. Molecules also can potentially have very low power demands, and many of us are thinking about how do we get even lower energy demands out of these kinds of molecules for different purposes. There are billions and billions and billions of molecules, and in principle, they can be embarrassingly parallel. And I'm not sure that we've all realized that potential, but in principle, they can be. So one example of this on the right that I give is just of storing information in a beaker of water. Now, if we were able to actually store information in all of the water molecules, and that's a big if, but if we were, then we'd be able to essentially store 200 Empire State Buildings worth of 1 terabyte hard drives in a beaker of water. And so that sort of shows the scale, the power, if you were in fact able to do that with molecules that are so small. The other reason why you might want to use things like molecules is because you may want to be thinking about different kinds of environments than in silico. So in soft robotics and responsive materials, you may want to actually do all of your programming in the molecules themselves so that you don't have to have any sort of external devices mediating the computation. So you might want to make a responsive fabric, a crawler, other kinds of polymers that might just do what you program them to do from the outset without any external devices. And of course, biology is essentially one big wet molecular computer. If you think about all the different kinds of biology that go on, biology is based on, yes, big polymers, but it's also based a lot on small molecules. So if you think about things that happen in the rhizosphere at the roots of different plants, that's almost essentially all small molecule where plants are transmitting signals to each other through those small molecules. So there are a lot of reasons for thinking about small molecules in life. Of course, DNA is usually the thing that we go to when we think about storage and computation, just because of the fact that it is the primary molecule that stores things in our bodies. But what we'll talk about is how do we go beyond DNA, maybe think about other kinds of storage that I'd say complement DNA in our bodies and elsewhere. So what I'll discuss is how do you compute and store using small molecules? What are the trade-offs that exist for that? So what we'll see is that when you use small molecules, you're talking about unordered mixtures of molecules instead of ordered polymers. You'll also see that these kinds of computing and storage tasks put huge amounts of pressures on the kinds of synthesis and detection that we can do. And so whenever you need to store information, you have to do some amount of synthesis. So I'll talk about what that actually looks like for small molecules. And maybe one thing that I'll note that we've realized is you really could use any small molecule to store and compute if you're smart. And so in some sense, it's more about getting a collection of molecules together than synthesizing them. And we'll talk about some what I'll call fundamentally molecular computations. So one of the goals of our work, see how far we get to it, is not to try to use our typical kinds of gates that you would think about in classical computation and put them onto molecules and imbue molecules with them, but it's instead to think about what do molecules and reactions do inherently and to use those operations to compute. So let's talk about how we would store information in disordered mixtures of small molecules. So as you know, whenever we want to store data, essentially we have long strings of ones and zeros. Each of those ones and zeros represents a bit, and each of those bits essentially represents two options. And so if you think about all of these sequences of digits that you might have, they store essentially 2 to the number of bits. There are 2 to the number of bits of possibilities for what those sequences can be. And when we want to basically store that information, we have to faithfully store all of those, the specific set of bits that we are attempting to store, and we have to be able to read out that very specific set of bits. So what we can do is we can think about how do we store those bits in chemical data, and then how do we exactly, highly faithfully read those bits out of the chemical data later on. And if you think about it, if we want to write chemical data, what we can do is we can assign each bit to either, historically people have used different kinds of monomers, but what we're going to do is we're going to assign each bit to an individual molecule in a solution. And the basic idea, and this is the basic idea, there are much more, I'll say, compressed ways of doing this, much more efficient ways of doing this, is that every bit corresponds to a molecule. And if the bit is present in a solution, and that solution can have any kind of solvent that can store the information, if the bit is present in a solution, that represents a 1 at that bit position. If it's absent, that represents a 0. And so in the simplest scheme, you can just take molecules, as long as you know which molecules correspond to which bit, which you map out at the very beginning. Then you can take those molecules, put them in a mixture, and that mixture can correspond to your data. Once you write that data, then you can think about, well, how could I read out all of those different molecular mixtures? And we spent a lot of time thinking about this. You might imagine that maybe you can use different kinds of spectroscopies. You can use mass spectrometry. You could use NMR. There are many, many different tools. But if you want to read a very dense spectrum, so if you want to store lots of bits in solution, you want to be able to read those all out all at once, the technique that likely works the best is mass spectrometry. So mass spectrometry is a technique where we can read out the exact masses of all of the molecules in our solution, and we can map those back to the different bits that we have. And so that's the basic setup that we use. Now, of course, one can imagine using other kinds of spectrometric or spectroscopic techniques, but that's the one that allows us to essentially store and read out the most data faithfully. So you might say, what molecules did you use or can you use to do this? It turns out that the answer is really any set of small molecules. I originally, when I was conceiving of this, I thought, why don't we use very special molecules that might be extremely good for storage? And so initially we used these, what we call OOGI 4-component molecules. So what an OOGI 4-component molecule is, what a multi-component molecule is it's a molecule that can assemble from multiple components. And it turns out there are a whole series of these multi-component molecules and reactions that can bring together, let's say, 4, 5, 6 different components. And the idea behind using these is that, you can imagine that each component has an R group that you can change. You can have different flavors of the R group. So if we have 4 components, I can imagine having, let's say, 10 R1, so 10 of R group 1 on the first component, 10 different R2 groups, and 10 different R3 groups, and so forth. And now you have essentially a combinatorial mixture of different possible compounds that you can make just from a set of, let's say, 40 different kinds of starting components. And so we originally used these multi-component molecules to store information because of the fact that we wouldn't have to do that much synthesis and wouldn't have to have that many components to make these. As it turns out, these molecules are also highly stable. So these are not biomolecules. And so they're not degraded by natural enzymes. There are really no enzymes that are just going to, wake up in the morning and degrade these things. And so these are extremely stable. They live in a deep free energy minimum. And so that's also quite useful for storage. It turns out that these reactions, and this is me, the stupid theorist, they actually almost give you 100% yield as well. So synthetic chemists know this. I didn't know this at the time, but it really is true. You throw these things in together, and they will form the product, which is great for doing things in a combinatorial and high throughput fashion. There are lots of possibilities for these molecules, however. So that was sort of our original go at this because we were trying to be clever. But maybe the more clever thing was to realize that we can actually use all different types of molecules. So we've used metabolites, catalysts, phenols. We recently used actually lab waste. One of our most recent papers was just going around the university and collecting lab waste. I mean, the point is that if I know the molecular signatures of the molecules in that waste, then I can just use it for information storage. So I really can use anything. So just as a practical example of how this works, if I have some set of words, let's say Rhode Island ACS, and I want to store those, I would convert that into binary. And then from binary, I would assign a molecule to each bit. Again, this is the simplest sketch so that you have an idea. So maybe the first bit is molecule 1 on the left here. The second bit is molecule 2 and so forth. And these differ from each other chemically so that when we mix these together, I can easily detect which one's which using, let's say, mass spectrometry. Now, there is a trade-off here. One can imagine a situation where you just throw all your molecules all in one mixture. That would be a lot of molecules if you did that. Or you can split the molecules into smaller sets and use a bit of physical space. And what we've realized over the years is that while one mixture feels highly compelling and highly compact, which it is, really the best thing to do is to mix physical space with the molecules that you're putting in solution. So the best thing to do is to make mixtures that have a certain depth. And so maybe that's 100, 1,000 different kinds of molecules. And then to put them in different positions, typically on a well plate, so that you can read them. And the reason why we want to do that is we want to decongest our spectra. So as good as mass spec is, you don't want an absolutely full spectrum so that you can't figure anything out. And this also makes it nice in terms of the synthesis. Again, we don't necessarily have to have billions of different molecules in one mixture. We can come up with thousands that work really well and then store information. And then, like I said, we can use high performance mass spec to read out what that information is. So I'll skip the workflow video for today. Happy to show it, but let me give you some ideas of some of the information processing things and machine learning things we have to do in order to understand this. So when we store our molecules in mixtures, what we want to do is read them out using mass spectrometry. And if you know anything about mass spectrometry, what it does is it basically tells you, right, the mass of each molecule. But again, me as the stupid theorist, I always said, well, it should just give you, one mass for the molecule, maybe an isotope's mass. Turns out that mass spec gives you actually lots of peaks, lots of different information about the molecules, which come from isotopes, which come from different kinds of sodiated versions. And a lot of times these molecules also absorb onto different kinds of molecules that might just be in your apparatus. And so you actually end up for every molecule with multiple peaks. And sometimes it's not clear which of those peaks is actually the prominent one. So you might say, oh, the original molecule's mass should be the prominent mass. And that's actually not true in these kinds of spectra. So what that leads to are relatively crowded spectra. So this is an example of, let's say, storing 32-bit data in Oogie molecules. So we'd store these 32 bits. We hope to see peaks for the masses of the molecules that we actually stored. And you can see that this spectrum starts to get relatively congested. This isn't insane, but we have to think through what all these different peaks mean. And so what we realized and started to use is machine learning. So you can imagine that every molecule can be associated with a variety of different peaks. And we don't necessarily know what all those peaks are. We can guess that maybe the molecule is associated with a proton or sodium or other kinds of species, but we don't actually know all of them and we don't know their intensities. So what you can do instead is sort of train on these different spectra. You can say, I have a molecule and it now generally has this kind of spectrum with these variety of peaks. I can machine learn what those spectra look like, and then I can apply it to large sets of mixtures so that we can pull out, given all these many, many peaks, what the mixture has inside of it. And so we decided to use different kinds of machine learning techniques. Here we were essentially using random forest regressions, random forest tests in order to determine which peaks we would have. And so this is an example on the left of if we were trying to store a variety of different molecules and a bunch of different information in different guanosine peaks and what would happen there. And it turns out, in the case of guanosine, that actually the sodiated peak is the prominent peak. And if we try to figure out all these peaks by hand, it would be impossible. But what we can do is we can use random forests to say what are the most common peaks. So in this kind of middle plot here with the decoded error rates and the raw error rates, what we do is we can say what is the error of pulling out what the information we stored was based on just a single peak. That's what people would traditionally do in the field. They look for one peak for one molecule, and that would be the red dot. And we see that that has a relatively high decoded error rate. But if instead we use this multi-peak analysis where we use machine learning to determine what are the most likely peaks associated with a molecule, we get the blue, and the blue has a much lower decoded error rate, almost to the point of 0. And this might sound obvious to you as information theorists, but when we talk to chemists, every chemist, and I think synthetic chemists are trained to do this, where they wake up and they say, well, why should you ever have any error? Error shouldn't exist. It never exists. Why would you want to resolve error? You should just make the molecules and you should be able to detect them. But the point is, when you're storing things with so much depth, you're inherently going to have errors, and you should be thinking about ways to suppress that error. So suffice it to say, we were able to store lots of different images up to essentially, this is an example of gigabytes of information, but we've already gone to terabytes. I show this plot just as an example. So we have been working with non-genomic data, right? We're using small molecules. And so we can get these blue points up into the red region. Now, yes, this is on a powered scale, a log scale essentially. But we are able to demonstrate a reasonable amount of storage. This is sort of an older piece of data, but we can go readily into the terabyte regime without much cost. We don't have to synthesize anything. We just have to really take mixtures. The key caveat of this information storage technique is really our ability to write things. So we can read really well with the mass spec, but writing can be hard just because of the fact that you do have to bring collections of molecules together. There are ways to get factors of 4 or 5, but really the slow part is bringing these molecules into one place and mixing them in the way that you want. And so that's really the engineering challenge for scaling these kinds of things up. Now, one thing before I get to the computing, which I'll go through quickly, is just to say, when we do this storage, we are thinking along the axis of monomer diversity. So you can imagine doing storage along 2 dimensions, maybe polymer length and monomer diversity. And we know that protein and nucleic acids have different monomer diversity, different polymer lengths. And we've been following with the small molecules, you follow the monomer diversity axis. But what you can imagine is that really, if you want the largest capacity, you should be increasing both your polymer length and your monomer diversity at the same time. So this is sort of giving you a different axis to think about things. Now, let me go into computation. That's probably the more interesting part for you. So I'll just give you a quick setup. We have lots of experiments in this area. What we've been trying to do using these small molecules is basically set up molecular machine learning. And the simplest case of that is the molecular perceptron that we can make. So for those of you not familiar with perceptrons are binary classifiers. What they do is they take in data and they say, does it belong to group A or does it belong to group B? Is it a cat or is it a dog? And fundamentally, the way a perceptron works is it takes a bunch of inputs, it weights them, it sums those weighted inputs, and then it passes that weighted sum through some kind of activation function. And so you can choose whatever activation function reasonably works in your kinds of networks. And then it gives you your output. Now, what we realized is that chemistry almost automatically does this multiply accumulate. Whenever you have concentrations of species, the species are inputs, the concentrations could be their weights. We've been working in that framework, but you can also imagine that rates can also be weights. And I know people here have worked on that. So chemistry automatically does multiply accumulate. Activating that multiply accumulate is a little bit trickier. But what we've also realized, and I spent more time than I should ever admit trying to figure out how to do this. So it's not just a threshold on a log scale. That's actually what many things in chemistry are. A real activation function would show some kind of nonlinearity in the chemistry. And the way that you can achieve that we've used is using autocatalysis. So an autocatalyst starts at a low concentration of things, then it produces itself, which leads to a ramp up, which is a nonlinear function. So we've been making different devices that basically do machine learning like this using molecules that use multiply, accumulate in concentrations, and then put that through activation functions, which are essentially autocatalysts. So let me show you a couple of quick computing examples just to cut to the chase. This is one of our most recent architectures that we've been using. It's kind of a workhorse we've been using in the lab to show how to do this. So if we want to use autocatalysis, we need an autocatalytic reaction. If you don't know any chemistry, this is one such reaction. It's called the copper catalyzed azide alkyne cycloaddition reaction. People will know this as a click reaction, won the Nobel Prize recently. The basic idea is, again, you start with a reactant, and that reactant can actually catalyze itself. So if you have little catalyst or reactant, it's going to react slowly, but eventually ramp up as it's produced and ramp up faster and faster until essentially it saturates. And you can see that this does, in fact, look like many of the kinds of nonlinear thresholds people use in ML. So we can do that in the lab. And one example of this is we did a winner-take-all neural network. And the idea is that we can plate an image in the catalyst. So there's these blue little cells here represent where we would plate a catalyst. And so this is supposed to represent an image from, let's say, the Caltech silhouettes. And we can train a network offline. And I don't have slides here. I can tell you how you train things chemically as well. But you can train a neural network offline to try to recognize this image. And then we can take the weights from that network and encode it into the concentrations and volumes of our molecules, and then use that to recognize this network. So we're using catalysts here. And the idea is that if our network is designed to, let's say, recognize the anchor I show here, then by plating and moving these catalyst pixels according to the volumes of our network and replating them and pooling them, then images that are the anchor that the network is supposed to recognize will threshold the first. And so you can plate lots of these different images, and what we can ultimately see is that once you plate and you apply the neural network, you'll see that the image that matches what the network is supposed to recognize will threshold first. And so here's a quick example of that. So here we wanted a network that would recognize starfish. So we would program a neural network to recognize starfish. Then we would move our catalyst volumes around according to the network weights. And then we would, in fact, see that our autocatalysts for the network that recognize starfish for the dish where we actually used autocatalysts in the starfish configuration would threshold first. And so that's an example of using catalysis in order to represent neural networks. Suffice it to say, there are issues with that we've been resolving. So this was one layer, only positive concentrations. You want to do a neural network, you have to go further. And so maybe for the sake of time, I'll leave you off with, we have thought about how do we develop this autocatalytic logic, and we've done this experimentally to show how we can do this with many layers, with negative weights, and in all different kinds of forms to recognize neural networks. So suffice it to say, I think I've shown you today some ways of storing information using small molecules and some possibilities for computing. So I showed you ways of using machine learning and implementing that in small molecule chemistry. We're working very hard on different aspects of this these small molecule neural networks. What I ask this community is we're still actively thinking through how do we improve the thermodynamic limits of these networks, and how do we think about what is computable, what is not through our architectures. And those are all questions that I think this community can help resolve. So with that, I'll thank my team. So this was a DARPA team that I led that did lots of the experimental work, and as well as my group. Many people from my group who are now faculty spent time thinking about this project. So with that, I'd like to thank you, and I'm happy to take any questions.